Uno, dos, tres, cuatro.
Hi everyone, welcome to Graphing and Solving Radical Equations. We're going to focus a little bit more on solving radical equations. We did graphing last class, and there's not too much more that's going to happen here. We'll look at it in context of some x-intercepts and y-intercepts, but otherwise we're going to focus on more of the algebra part of this. So some of this may seem like some review from Pre-Calc 11, and what we want to be able to do is we want to be able to solve for x when we have some sort of radical. If you look at the first example right here, we want to isolate our radical. We have our steps listed above here, and if we add 2 to the other side, we would get root 5 minus x equals 2. Once we have our radical isolated, we can eliminate the radical by squaring it, because the opposite of a square would be a square root. So they'll reduce with each other, and then whatever you do to one side, make sure you do to the other side. So based off of that, we would have 5 subtract x equals 4, and then we can solve for x. So in this case, I'm going to add x onto the right side, and I'll subtract 4 onto the left side, and we have x equals 1. Once we have that, in most cases, everything will be okay, but we need to make sure that we do one final step. We have to check to see if we have an extraneous solution. So an extraneous solution means that you've done all of the correct algebra, but for whatever reason, your solution doesn't work out. So if we take a look at our original and we go back to root 5 minus x minus 2 equals 0, we should put in and substitute 1 for x. And we want to make sure that the left side balances out with the right side. And in this case, it does. So we can feel very confident that our solution is x equals 1. Now, if you have access to a graphing calculator for something like this, what you could also do is potentially you could put root 5 minus x minus 2 in for y1, and you could find the 0. You could find the x-intercept, and you'll get a solution of 1 there as well, and that's a good way to ensure that you've done this correctly. For the second question here, again, we want to isolate our radical, so let's add x onto the other side. And then we could square both sides. And then we want to isolate it, but in this case we have an x squared and we have an x term. So let's bring everything onto one side and make the other side equals to 0. And I think it'd be best to bring everything onto the right side because we have a positive x squared there already. So let's subtract x, and let's subtract 6. And then we'd be left with a quadratic that we could factor here. So we have x minus 3 x plus 2, and we would end up with a solution where we get x equals 3 and x equals 2. Sorry, negative 2. Once again, we want to be able to do a check here, and we want to make sure that everything is all good. So you should go back to the original and you should sub it in and see what ends up happening from that. If we take the 3 and we sub in 3 for x, so let's go x equals 3. We would get the square root of 9 minus 3 equals 0. So yes, that works, and I feel very good about x equaling 3. But if we put in the negative 2, I have a feeling that this might not work here. So if we go x equals negative 2, so we have root negative 2 plus 6 minus negative 2, we would end up with the square root of 4 plus 2 equals 0, and we would get 4 equals 0, and that is not equal to each other. So because of that, even though we've done the correct algebra, we have to reject negative 2, and we say that negative 2 is an example of being an extraneous solution. Let's move on to the next example. Solve algebraically and round the solution to two decimal places as well as giving an exact solution. So just to refresh ourselves on exact solutions, that would mean leaving it in an exact radical form. And they've given us the quadratic formula, which means that probably we're going to have to put it in the quadratic formula because whatever we end up with might not be factorable. Our steps are exactly the same. Let's look by isolating our radical as a first step. So we can add x onto the opposite side and we can subtract 2. Then let's square both sides to eliminate the radical. We have x minus 2 squared, so we can FOIL that out. We would get x squared minus 2x plus 4. So I'm just going to write that out a little bit faster. We get x squared minus 4x plus 4. And similar to 1b, we want to bring everything onto one side because we have an x squared and an x term, and it looks like it'd be better to bring things to the right term to keep our x squared positive. So we could subtract x and we could subtract 1. And we would get x squared subtract 5x plus 3. Definitely what you want to do is see if you can factor that, find two numbers that would multiply to 3 and add to -5, and we would quickly see that that can't happen. And so because of that, it doesn't mean that there's not necessarily a solution. It's just not something that would be a rational number. So we can take this and we can put it in our quadratic formula. So we know our a value is 1, our b value is -5, and our c value is 3. And if on the right side here we put this in, we could say x equals 5 plus or minus -5 squared minus 4 times 1 times 3 all over 2a. I like to express this root just all in one step. So we'd say 25 minus 12, we get root 13 over 2. And that gives us two separate solutions. So solution number 1 is saying that we have 5 plus root 13 over 2. And then our second solution here is saying 5 minus root 13 over 2. And it asks us to also write these as to two decimal places. So we should get our calculator out and we should see what we get from something with this. So we say right here, we could go 5 plus the square root of 13. And we want to divide that by 2. And we get, whoops, 4.3. I did that wrong, so I'm just going to do that one more time here. You get 5 plus the square root of 13 equals, and take that and divide it by 2. There we go. Okay, so we get 4.30 as our first solution. And then let's try that again. And let's go 5, subtract the square root of 13. Divided by 2. And we get 0.70. Okay, so let's go back here. So we had 4.30 and 0.70. Okay, and that's what x equals. Whereas, remember, these are exact solutions, and this would be a rounded two decimal place solution. Okay, so a trick here now is to see if whether or not both of these are accepted or rejected. And so if we take a look at this, I'm going to try something a little bit different on the check here just to show maybe a bit of a shortcut. Again, I would encourage you to use your graphing calculator to be able to graph it, and you would see that there's only one solution in this case. So where we had root x plus 1 minus x plus 2 equals 0, our original, we can put it in here to substitute to see where our solution is going to be. Or as an alternative, you could also substitute it after you've isolated your radical. And sometimes subbing it in this part here, this stage where we've isolated our radical, is a little bit more efficient, because if I was to put in 0.70, if I was to substitute that in here, I would have something where my radical, my left side, would be equal to 0.70 minus 2. It'd be equal to negative 1.30. And I know that my radical can't be equal to a negative number, so I know that that doesn't work, and I'd be able to reject it based off of that premise just by looking at it. And if you subbed it into the original and you kept things simple, that absolutely works as well. When you do sub in 4.30 and you put that in there, I'm just going to eyeball it right here, and I'd say the square root of 5.30 is going to be something that's going to be around 2.3. So I feel pretty good about that. You could graph it to confirm that, but we're going to accept this solution and we're going to reject the solution that doesn't work. Okay, we're on to our final example for the day already. So now we have something that's given in a context of a y equals, but they're asking us characteristics about it on a graph. So they're saying, what would be the y-intercept? Well, we know when we want to find a y-intercept, we know that x equals 0, and we know when we want to find an x-intercept, y equals 0. So for part A, if we want to make x equals 0, then we could just say y equals root root 1, which is just 1, and then plus a 4. So our y-intercept is just going to be 5. If you want, you could do a check of that, but I think we feel pretty confident that that's going to work out just fine. Okay, so let's look at the next part right here. If we want to find the x-intercept, we can now put in 0 for y. So if we have part B here, we could say 0 equals root, and we want to say it's going to be root x plus 1 minus x plus 4. So let's add x onto the left side, and let's subtract 4 to isolate for our radical. So we have x minus 4 equals root x plus 1, and then we should square both sides. And I'm going to FOIL the left side quickly. We'd get x squared minus 4x plus 16 equals x plus 1. Then we want to bring everything onto the left side, so we would want to subtract x, subtract 1, subtract 1. And we would get something that would say x squared minus 9x plus 15 equals 0. This question is pretty tempting to think that you might be able to factor it, but it doesn't work. 1 and 15, no combination of that. 5 and 3, no combination of that. So it's not factorable, but once again, that doesn't mean that there's not a solution. So we can throw it in the quad. So let's put this in the quad quickly. We could say x equals negative b, so negative 9, plus or minus the square root of b squared minus 4ac all over 2a. And then we can see what that simplifies to. So we get 9 plus or minus 81 minus 60, so root 21 over 2. And now that we have something like that, they're saying between, well, I guess let's first answer part B, and let's say our x-intercept, the exact form of our x-intercept, looks like it's going to be this. So I guess I would say, I don't know if we can confirm that, or if we're going to say, are there 2 x-intercepts, or is there just 1 x-intercept? So let's look back to our check, and let's see what we could do potentially with adding, looking at it in the form where we have our radical isolated. So let's look at it at the form, where we had x minus 4 equals root x plus 1. So this is after you've put in 0, you want to see what would happen there. And I'm going to say that we should probably figure out what our 2 solutions are as decimals to help us out with that. We know that we're saying something with 9 plus the square root of 21 over 4 and 9 minus the square root of 21 over 4. Okay, so again, let's take out our calculators and let's just confirm that here. So 9 plus the square root of 21 divided by 4. So we get approximately 3.40. Okay, and then let's also do 9 minus the square root of 21 divided by 4, and we're going to get 1.10. Okay, looking back now here, if we take a look at this, if we put in our values right here, let's see what would end up. Oh, do you know what? I have a little bit of a typo here. This was just divided by 2, and this was divided by 2. Whoops. So these numbers actually, let's go back here. 9 plus the square root of 21 divided by 2. Okay, and I know I probably could have just doubled that, and I know that it'd be 6.8, and I'm guessing the other one here is going to be 2.2, but let's just do that just in case. So 9 minus the square root of 21 divided by 2, and we get 2.21. Okay, so given those decimals, if we look back here, and they're saying, well, if I was to do a check, I know that if I put in 2.21 for x right here, I would create a negative number on the left side, and I know that that negative number could never be equal to the right side. And so because of that, the 2.21, which would come from this 9 minus root 21 over 2, has to be rejected. And if I sub in 6.80 and I put that in, just eyeballing it, but knowing that if I did a full check of that, that will work. So for your x-intercept here, we'll have 9 plus the square root of 21 over 2 comma 0, and that's our exact x-intercept. And then if they want to find out as a decimal, we know that that was equal to 6.80. And so part C is worded a little bit strange. They're saying between which consecutive integers would the zeros of the function occur. And so if the answer is 6.8 for x, then the integers would be between 6 and 7. Okay, and then just as one final thing here, you've heard me a couple times reference, you can always check this by graphing it. Let's look at the very original part here. So y equals root x plus 1 minus x plus 4, and let's put this into the graphing calculator. So here we go. Let's clear this, and let's go y equals root x plus 1 minus x plus 4. And I'll just zoom 6 it, and it looks like we have something where we have one intersect that you can see a little bit of right here. So let's see what would happen if we try to trap that right here. So we could go second trace, and let's find the 0. And if we do that, we get 6.79. Okay, well, that was pretty close to the 6.80 that we had right there. So I feel pretty good that we found the right solution for that. Okay. All right, well, that's all that we have for today. So we're going to assign page 172. You can see the homework down here below. But hopefully it's a pretty straightforward lesson from things that you've seen from Pre-Calc 11. Thanks.